A necessary and sufficient condition for a code to be instantaneous is that none of the code word in the code should be a prefix of another code word in the code. Let us try to prove this. Now, the sufficient portion of this test is very clear from the definition of the instantaneous code. If we have a code word which is not a prefix of another code word, then we can decode the sequence of code symbols in a direct manner. Let us say that when we receive the code symbol sequence, then we start scanning this sequence until we reach the subsequence corresponding to a code word. Now, this subsequence must correspond to some code word, because we have made the assumption that none of the code word is a prefix of another code word in the same code. So, as soon as we receive the subsequence corresponding to a particular code word, we can decode it as that subsequence belonging to a particular symbol in the source alphabet. So, there is no time lag in the decoding process. To prove the necessity portion of this test, let us assume the contrary, and in order to prove the necessary portion of this test, let us assume a contrary and derive the contradiction. So, let us assume that I have a code word xi which is a prefix of some other code word xj in the code. Now, when we receive the code symbol sequence, then when we come upon the subsequence corresponding to the code word xi, then at that instant we are not sure whether that subsequence belongs to the xi or xj, because we have made the assumption that xi is a prefix of xj. In order to make the decision, we have to observe few more code symbols in the main sequence before we take the decision. So, what it means that there is a time lag in our decoding process, and therefore, the code is not instantaneous. So, we started with the assumption that if xi is a code word, a prefix of another code word xj, then the code cannot be instantaneous. So, this proves both the necessary and sufficient condition of the test, that for a code to be instantaneous, no complete code word of the code should be a prefix of some other code word. Now, let us summarize what we have talked about the codes. In summary, we can say that we have a class of all codes and out of all these codes, we are interested in a subclass of all these codes, and that is non-singular codes. We have also seen that just the constraint of non-singularity is not sufficient for us to decode the sequence of code symbols. So, what we want, that code should be also uniquely decodable, and that forms another subclass of non-singular codes, and this is a subclass, and that is uniquely decodable codes. And finally, we said that what we would be interested is in another subclass of this uniquely decodable code, and that is instantaneous codes. So, let us summarize all this with the help of a simple example. So, let us assume that I have a source consisting of 4 source symbols, and for this source I have different codes. One code is where the code symbols for this source symbols are 0, 0, 0, and let us assume once that our code symbols come from the binary code alphabet. So, if this code is a singular code, because for each of this source symbol the code words are not unique. Another one would be 0, 0, 1, 0, 0, 1, 1, 0. So, this I would say it's an example of a singular code where all the code words are same for all the source symbols. This is an example of a non-singular code, but when I receive 0, 1, 0, then I am not able to decode it in unambiguous manner, because 0, 1, 0 could either corresponds to S2 or it could correspond to S1 followed by S4, or it could correspond to S3 followed by S1. So, this is another example of a not uniquely decodable code, but this is non-singular, not uniquely decodable. Another example would be 1 0 0 0 1 1 1 1 0. This code is uniquely decodable. But this code again is not instantaneous. When I receive code symbol sequence, then when I have 1 0 or 0 0, I can uniquely immediately identify this subsequence 1 0 0 0 as either S1 or S2. But when I receive a subsequence in this sequence of code symbols where the subsequence is 1 1, then immediately I cannot decide. I have to see basically what follows this one. If 1 follows after this, then I can be sure that this subsequence corresponds to S3. But if a 0 follows, then I have to check for the number of zeros which follow after this one. If there are even numbers of zeros following after this one, it means that this subsequence 1 1 must be S3. But if there are odd numbers of zeros following this one, then what it means is that 1 1 and the next 0 would be S4 and other zeros would be decoded as S2s. So, I have to observe the future symbols when I receive 1 1. So, I cannot decode immediately. So, this is an example of a non-instantaneous code. And finally, I have 0 1 0, 1 1 0 and 1 1. This is an example of instantaneous code. In the light of what we have discussed earlier, we see that none of the code words in this code is a prefix of another code word in the same code. Now, in order to appreciate the nature of constraints on the code when we want to have this code as instantaneous, let us make some primitive attempts to synthesize an instantaneous code. So, let us say that I have a source consisting of 5 symbols. And I am interested in designing or synthesizing a binary instantaneous code. So, my code alphabet is assumed to be binary and it is 0 1. So, let us start the synthesizing this binary instantaneous code. One way in which we could start is that I can assign 0 symbol to the source symbol S1. So, my first code word consists of length 1 and it is a code symbol that is 0 assigned to S1. Now, for code word which is to be assigned to S2, I cannot start with 0 because that will violate the condition for the instantaneous code. So, the only alternative left for me is to start with 1. Now, again I cannot assign a single code symbol 1 to source symbol S2, because if I did that, then I will be exhausted in the sense that I will not have any more symbols to start my code words for other source symbol S3, S4, S5 if I want my code words to be instantaneous. And for the code words to be instantaneous, none of the code words in the code can be a prefix of another code word. So, I cannot assign 1 to S2. So, the only alternative left for me is to use 1 0. Now, once I have assigned 1 0 to S2, what is left out is I can use 1 1. Now, if I have 1 1, again I cannot solely assign to S3, because if I did that, then I will not be able to form the code words for S4 and S5 in a way where S1, S2, S3 will not be a prefix. So, one way to assign S3 would be 1 1 0. Now, what is left out would be 1 1 1. Now, I have 2 more symbols. So, again I cannot assign just 1 1 1 to S4, I can assign 1 1 1 and 0 to S4, and finally to S5 I assign 1 1 1. So, this is one way of synthesizing an binary instantaneous code, where I started with a code word length of 1 for S1 and reached to the code word length of 4 for both S4 and S5. Now, from this example, it is very obvious that when I start with fewer symbols initially, then for the code words or for the later code words, the length of the code word increases. So what it means that if I were to start with more number of code symbols for my starting source symbol, then I would have had more freedom to choose my code words for my later source symbols, and probably what would have happened that my later code words would not have been so large. So let us try to test this conjecture with synthesizing another binary instantaneous code where I assign two symbols, code symbols, to my first source symbols as 0, 0. Now once I have assigned two code symbols 0, 0 to S1, I have three more possibilities which I can use as an assignment of code words for my remaining source symbols. Now since I have 4 more left and I have 3, I cannot assign all the remaining code symbols of length 2 to S2, S3, S4. So what I will do basically is assign to S2 as 0, 1, to S3 I will assign 1, 0, to S4 I cannot assign 1, 1, because if I did that, if I assign 1, 1, then I would not have anything remaining to be assigned to S5 in a way where none of these code words form a prefix. So the only way for me to assign S4 is 1, 1, 0, and now for S5 I can assign as 1, 1, 1. So this is another code which I generate. This is another binary instantaneous code which I have generated. Now if I call this code number 1 and if I say this is code number 2, and if I ask the question that which of the two code is better, then I cannot answer this question based on the information given to me so far. Okay. So it is not, but one thing is clear, that when I use smaller code word lengths for the assignment of the initial source symbols, then the code word lengths which are left for the assignment to the later source symbols will be larger. So this is an example out here. But when I start with a larger code word length for the initial symbols, then I get more or less balanced code word lengths for all the source symbols. So in the construction of an instantaneous code, the shorter we make the first few code words of the code, the longer we will have to make the later code words. By using 0 as a code word in the first code word, we restricted all other code words to starting with 1. Whereas in the second code, when we use 0, 0 as the first code word, in this case we were able to form later code words by starting with 1, and in addition we could also use code words starting with 0, 1. So these examples help us to understand the constraints which are imposed when we try to design an instantaneous codes. Now what we have seen so far is qualitatively we have looked at the constraints on the code word lengths of an instantaneous code. Now the same constraints can be put in a quantitative fashion, and that is being done by what is known as Crafts inequality. So Crafts inequality gives us a quantitative constraint on the word lengths of the code words which we can use for an instantaneous code. So, let us look at the Crafts inequality. So, consider an instantaneous code with source alphabet S equal to S1, S2 up to SQ and code alphabet, this is R symbol code alphabet. So, I will have X1, X2 up to X star. So, with the help of this code alphabet, I form code words for this source symbol. Let me identify this code words as X1, X2 and XQ. Now, each of these code words is a sequence of code symbols chosen from code alphabet X. So, each of this will have a length. So, L1, L2 and LQ. L1 means there are L1 number of code symbols from this code alphabet which forms a code word X1 for the source symbol S1, and similarly LQ means there are LQ number of code symbols from this code alphabet X which make up the code word XQ for the source symbol SQ. Okay. Now, it is often desirable that the lengths of the code words of a code be as small as possible. So, now necessary and sufficient condition for the existence of an instantaneous code with code word lengths given by L1, L2, LQ are provided by the Craft inequality. So, what is the Craft inequality says that a necessary and sufficient condition for the existence of an instantaneous code with code word lengths L1, L2, LQ is that where R is the number of different symbols in the code alphabet. So, this is the Craft inequality. Now, before we try to prove this Craft inequality, it will be instructive to look at some examples and see how we might utilize this inequality to decide whether a given sequence of code word lengths can really form the code which is instantaneous. So, with that, let us take a simple example. So, if I have source S consisting of S1, S2, S3, S4, 4 symbols, for this source, let me assume that I have a code which is 0 0, 0 1, 1 0, 1 1. Let me say that this code is A. There is another code I have 0, 1 0, 1 0 0, 1 1 0, 1 1. This is my code B. I have another code C which is 0, 1 0, 1 1 0, 1 1. I have another code D which is 0, 1 0 0, 1 1 0, 1 1, and finally I have another code E which is 0, 1 0, 1 1 0 and 1 1. Now, if someone gives me these codes, 5 codes for this source, and if the question was to find out whether these codes are instantaneous or not, then Craft equality by itself cannot help me to decide whether code is instantaneous or not. Yes, what the Craft inequality helps us to find out whether the code word lengths which I have chosen are reasonable choice for instantaneous code. Let me take a simple example to explain this. Now, we will try to evaluate the Craft inequality for each of these 5 codes. So, we are interested in evaluating, since our alphabet in this case is binary. So, the value of R we have is equal to 2. So, the Craft inequality will become 2 minus Li, I going from 1 to 4. So, let us try to evaluate this expression for each of this code. So, for the code A minus Li, I is equal to 1 to 4 will give me as 2 minus 2 plus 2 minus 2, because each code word is length 2. So, what I get is equal to 1. So, this satisfies my Craft inequality, which says that this quantity should be less than or equal to 1. Now, because it satisfies this Craft equality, I can be assured that I can have code word lengths of 2, 2, 2, 2. So, all the code word lengths can be of equal length 2 for this case. But so just because this inequality is satisfied, it does not mean that a code words are chosen appropriately for the instantaneous code. In this example, if you examine the code words for this code A, they are also instantaneous. Correct? So, it is important to note that the Craft inequality is the restriction on the word lengths of code and not on the code words itself. So, this is we get, and this code is both instantaneous and it satisfies the Craft inequality. Let us try to evaluate the same inequality for the code B. For the code B, what I would get is, if I try to evaluate this, 2 minus Li is coming out 2 minus 1 plus 2 minus 3 plus 2 minus 3 plus 2 minus 3. This turns out to be 7 by 8, and again this is less than or equal to 1. So, what it says that code word lengths of 1333 are acceptable as the code word lengths for instantaneous code. Again, if we examine the code words of this code, you will find that they are instantaneous. Example of C is equal to 2 minus 1 plus 2 minus 2 plus 2 minus 3 plus 2 minus 3, and this turns out to be 1. Again, this is less than equal to 1. So, again this length, code word length of 1, 2, 3, 3 is acceptable. And again, if you examine this code words for C, it turns out to be instantaneous because none of these code words are a prefix of other code word. And code C was actually obtained from code B by dropping code symbol 0 from the second code word. And finally, let us look at the code D. Now, this code D is been obtained from code B by just dropping a symbol, code symbol 0 from the last code word corresponding to S4 in the code B. Now, for D, if you evaluate, this expression, it turns out to be 2 minus 1 plus 2 minus 3 plus 2 minus 3 plus 2 minus 2, and this turns out to be 1 is less than or equal to 1. Now, again, this is very important to note that what it says that the code word length of 1332 is acceptable. Right? Same out here, it was 1, 2, 3, 3. But if you examine this code D, it is not instantaneous because code word corresponding to S4, that is X4 here, is a prefix of a code word X3. So, in no way this can be instantaneous code, but the code word lengths are acceptable as instantaneous code. And finally, if you look for the code E and if you evaluate this expression, we get as 2 raised to minus 1 plus 2 raised to minus 2 plus 2 raised to minus 3 plus 2 raised to minus 2, and this turns out to be, now this is greater than 1. Now, as soon as I have this inequality not satisfied, that is, I can immediately say that I cannot have this as instantaneous code because the code word length itself violates the condition which is required for the instantaneous code. Before we look into the proof of the Crafts inequality, let us consider one more example to appreciate the constraints which go in the synthesizing of an instantaneous code. So, let us assume that I have a source consisting of 10 symbols, and those 10 symbols could be decimal digits from 0 to 9, and I am supposed to code this source with a binary alphabet. And let us make one more assumption that for some reason the occurrence of 0 and 1 is very frequent. So, I want that when I form the code words for the source symbols 0 and 1, the code word lengths corresponding to this code word should be as small as possible. So, let us assume that for my source symbol 0, I assign the code word which is 0, and for my code source symbol 1, I assign the code word as 1 0. Obviously, I cannot just assign 1 because then I will not be able to form the instantaneous code. Now, for the remaining 8 symbols, what is desired that I form the code words which are of equal length. Now, I am interested in finding out what is that minimum length, minimum equal length which I can use for forming the code words for the remaining 8 source symbols, and I want to form an instantaneous code. So, to answer the question how short it is possible for me to make the remaining 8 code words, correct, assuming that all the 8 code words are of the same length. Now, to answer this question, we can take the help of Kraft's inequality. Kraft inequality says that this condition should be always valid, I is equal to 1 to 9 less than or equal to 1. Since we have made the assumption that the code word corresponding to symbol 0 is of length 1, so L0 is 1 and L1 is 2 and L2, L3 up to L9, the code word lengths for this code words are equal, and let us say they are L. Therefore, I get half plus 1/4 plus 8 times L less than or equal to 1, and this simplifies to L is greater than or equal to 5. So, what it says that if I want the remaining 8 code words to be of equal length, and if the code has to be instantaneous, then I cannot form a code which is of length less than 5. So, the minimum length I should have is 5, and it is easy to see that I can form such a code for this source. So, a binary code for decimal digits would be so this would be the instantaneous code where all the code words corresponding to a source symbol from S2 to S9 would be all equal length 5. Okay. Now, with this background, let us go ahead and try to prove the Kraft's inequality. So, the Kraft inequality, there are two portions, one is a sufficient condition and one is another is a necessary. So, first let us try to prove for the sufficient condition. So, first is sufficient condition. So, what sufficient condition says that if this is satisfied, then I should be able to construct instantaneous codes. So, let us assume that the required code word lengths are L1, L2 up to LQ. This code word lengths need not be the distinct. Okay. Now, it will be useful for us to consider all the code words of the same length at one time. So, let me assume that I have N1 code words of length 1. I have N2 code word of length 2. Now, let me assume that L is the maximum length of a code word. So, L is maximum of Li. So, if I assume this, then let me assume that NL corresponds to number of code words of maximum length L. So, it means that summation of ni's I is equal to 1 to L is obviously equal to number of code words which I can have. The number of code words will be equal to Q, and I have this condition now. Using this equation, we can rewrite this equation which corresponds to the Kraft inequality. I assume that this is true. So, what it means that there will be in this inequality based on this relationship here, I will have N1 terms corresponding to R minus 1, I will have N2 terms corresponding to R minus 2, and I will have NL terms corresponding to R minus L. So, based on this I can write this equation out here as so, given this and assuming the notations, we get this relationship. Now, if you multiply this both left hand side and right hand side by RL, what I get is now this forms the basis for a further discussion. Now, let us write out this equation and rearrange terms. So, if we write out this expression and rearrange terms, we will get NL less than or equal to RL minus N1 R L minus 1 minus N2 R L minus 2 minus N NL minus 1 R. So, let me say that this is equation number 1 A. Now, dropping the term on the left hand side and dividing by R, I will get as NL minus 1 is less than equal to R L minus 1 minus N1 R L minus 2 minus N2 R L minus 3 minus N L minus 2 R. So, you drop the term on the left hand side, bring this term out here and then divide by R. This is what you will get. Let us call this equation 1b. So, this way if you proceed, I will get N3 less than or equal to R cube minus N1 R squared minus N2 R. This is 1 C and N2 less than or equal to R squared minus N1 . And finally, I will get N1 less than R. Now, this set of inequality is the key to the construction of the code we seek, correct. Now, what this inequality says, that we are required to form N1 code words of length 1. Now, if we assume that our code alphabet is of size R, then there are R possible such code words that we may form using an R symbol code alphabet. And since the requirement is that N1 should be less than R, we can select these N1 code symbols of length 1 arbitrarily. So, if we do that, then we are then left with R minus N1 permissible prefixes of length 1, namely just those prefixes which were not used as code words. So, now these are the prefixes which we can use. Now, by adding one symbol to this prefixes, we will get code words of length 2. So, the number of code words which we can get of length 2 would be equal to this R minus N1 R, and that is equal to R squared minus N1 R. So, these are the code words of length 2 which we can form. Now, if you look at this equation out here, what it says that the number of code words of length 2 required is always less than or equal to R squared minus N1 R, and we have this available with us. So, as before, we choose our N2 code words arbitrarily from among these choices. So, if we choose that, the number of prefixes which will be of length 2 which will be left out would be R squared minus N1 R minus N2. So, this will be the unused prefixes of length 2. Now, using these unused prefixes of length 2, if we add one more code symbol, we can form code words of length 3, and that would be given by R cube minus N1 R squared minus N2 R. So, these are the permissible prefixes of length 3. Again, if you look at this equation, we are assured that we shall not need no more than this number, correct, and we select our code words of length 3 arbitrarily from among this. Now, we may proceed in this fashion until we have formed all the code words for our code. and all these equations assure us that at each stage we have enough prefixes left. So, based on this we can always form an instantaneous code. So, we have proved that if this condition is satisfied, then it is possible for us to form an instantaneous code. So, this is the sufficient part of the Craft inequality. Now, next time we will try to prove the necessary part of the Craft inequality. It is not very difficult, we have to just reverse our arguments, and we will have a look at this little more in depth in the next class.